let's remember what a function is. A function is just a mathematical equation that describes the relationship between variables. Here we're going to start with a really simple example of a total cost function. Total cost is equal to 5Q. So for this firm, if they produce 3 units, what will their total cost be? All we have to do is plug in Q to get the answer, and you can see that if they produce 3 units, their total cost will be 15. It's also pretty easy to plot the total cost function on your graph because it's a linear equation. And I know it's a linear equation because it follows the same general functional form as all linear equations. Hopefully you remember this from your algebra class, y equals mx plus b. I'll remind you that m is the slope of the equation and b is the y-intercept. So the y-intercept for this equation is 0, right? The line starts here at 0 because there's no b term. And what is the slope? It's 5, because that's the number here next to the q. And that's important because the slope of our total cost equation is our marginal cost. You might remember from your intro class that marginal cost is change in total cost over change in quantity. It's how much total cost increases as we produce each additional unit. Well, that's the same as slope. Remember, slope is rise over run. It tells me for every unit I move over on the x-axis, how much the line moves up on the y-axis. So the slope of our total cost function is 5, which is also equal to marginal cost. So in this example, because the slope is constant, we also have a constant marginal cost equation. And that means that no matter how much I produce, the cost of producing one additional unit is always 5. And in general, marginal functions in economics always refer to the slope of the original function. So if you wanted to find, for example, your marginal revenue function, what you're really asking is what is the slope of the total revenue function? And the easiest way to find the slope of a function is to take the first derivative. So you'll want to remember how to do that. And I've given you a math review handout to help. Everyone should review this handout. And you should remind yourself some basic rules of algebra and differentiation that we'll be using throughout the class. Here we have a slightly more complicated total cost function, but nothing too crazy. 10q squared plus 10. And we want to do the same thing. Think about the relationship between total cost and marginal cost. So for this firm, what will their total cost be if they produce 3 units? We just plug Q in again to get total cost. And we'll find that if they produce 3 units, their total cost will be 100. Notice that this equation does not start at 0. The y-intercept here is 10. And as we plot this equation, we can see that it is increasing, like any good total cost function. And it's increasing not at a constant rate, but here at an increasing rate. So the slope is no longer constant. The slope is increasing. And that will be reflected in our marginal cost equation. So to find marginal cost, we just need to take the derivative of the total cost function with respect to quantity. And when I do that, I get 2 times 10q or 20q. And then I can plot that on my graph to see that we were right. in fact, the marginal cost function is positive and increasing, reflecting the fact that total cost increases at an increasing rate. So one last thing here to sum up is that the first derivative tells you whether or not the function is increasing, decreasing, or neither, based on whether it is positive, negative, or zero, right? So the sign of the first derivative tells us about the slope of the function. If the first derivative is positive, we have an increasing function, as both of these total cost examples have shown us. If the first derivative is negative, we have a decreasing function. And importantly, if the first derivative is equal to zero, this should say equal to zero, then we have a local maximum or minimum. And this is important because we're going to be looking for these local maximums really throughout the course. So here I've got a little example graph where I've got a couple one local maximum, one local minimum. And I know that at both of these points, the function's not going up, it's not going down. The slope is zero. And I can think about what the first derivative looks like at other points along this function, just to kind of sum everything up here. On this portion of the line, the slope is positive, right? The function is going up. Here, the function is going down. So I know the slope is negative, and then it's going to be positive again. So I could actually plot what I expect the first derivative to look like in this example. I know it's zero at these 2 points, positive, negative, and then positive again.